So the next speaker is Linus Romer. I think he's some kind of a freelance font designer, and today he will talk about MetaPost using for creating curve comps and harmonized paths. I hope this one works.
Welcome to my talk on curvature comps and harmonized paths in MetaPost. I'm actually a math teacher in Switzerland, not a freelance type designer. Curvature comps and harmonization are two tools that are quite popular in font design software now. You see here a screenshot of FontLab 6. Curvature comps are used to visualize curvature along paths and curves, and harmonization is a way to make paths curvature continuous. And I will present implementation of both in MetaPost, which is a good method to make a reference implementation, because MetaPost has many tools to handle with Bezier curves. Here's how I got into it. I have designed several software implementations in FontForge. I did a harmonized tool and also balance tool. I've written some conversion tools for Metafont to outline fonts, and I also have designed some fonts in Metafont as well as in FontForge. It is crucial to know what curvature means. Curvature is the inverse of the radius of an oscillating circle. So let's say you have this curve given, and we want to determine the curvature at the very left end. Then we construct the oscillating circle, which means that the direction and the change of direction is the same as in the touching point of the curve. Here, let's say the radius is 2.6, so the curvature would be 1 over 2.6, which is 0.38 or something like this. And as we wander along this curve, you might notice that the oscillating circle becomes bigger and bigger. So the curvature becomes less and less. At the end, it's just the other way around. So here, it's the greatest curvature and the smallest radius of the oscillating circle. If we assemble all these red vectors, these curvature vectors, to one picture, we get this picture, which is called a curvature comp. We can even make it more dense, like this. And we can also fill the gaps with color and also change the color depending on the length of the vectors, which would look like this. So I will call this a curvature comp for the rest of this talk. And for the definition of a MetaPost macro, first of all, I need a cross product macro, because MetaPost supports a dot product macro, but not a cross product macro. So this is just a missing part. It returns the signed area of the parallelogram that is spanned by two vectors. And the macro for the initial curvature of a curve must look something like this. It begins with var_def curve of an expression p, where p is the path, and then it should return this red curvature vector. And I once thought that it would be a good idea to make curvature at the time t of a path, so that I could calculate the curvature at any time, at any travel time. So let's say in the mid of the curve. But of course, this would be a very bad idea for integer t's, because then it's not clear to take the curvature of the left or of the right part. So here is the math behind. I think many of you are quite mathematical affines. So MetaPost deals with cubic Bezier curves, which are defined like this by 4 points P, Q, R, and S, and the travel time that starts with 0 and ends with 1. And if we take the derivative and look at the time t equals 0, we get the derivative 3 times q minus p, which is substituted as v, and the same procedure for the double derivative, which here is called w. If we take a common way to calculate the curvature, which depends on the cross product, so I have already defined it, the cross product of the first and the second derivative divided by the length of the first derivative to the power of 3, and I substitute the things that I have defined before, so here the definitions of v and w, and also introduce a new variable L for the length of the first derivative. I will end up with this formula to the lower right. And if you wonder why I distributed the L's so strange, it's to prevent arithmetic overflow. But of course, you will never, the curvature could be infinitely large, so you still could run in an arithmetic overflow. Then you would have to load numerical packages for MetaPost. The special case where the first derivative is 0 is not handled here, but they're problematic anyway, but because it normally means that the curvature is plus or minus infinity. So the macro just does this, as what I said. It takes these variables and calculates it. I won't go very much into detail, because you could also read it in the preprint, for example. Then the macro for this curvature comp works like this. I have hardwired 50 sub-segments. Of course, you could change, but 50 seems to be a reasonable number. And you calculate subsequent curvature vectors k and c. You also want to scale it, because normally it wouldn't be visible when you have large coordinates. And the color depends on the average length of both vectors where it's in between. So here's the macro for the curvature comp. P is the path, S is the scaling factor. And I want to highlight two things. The one thing is this part, if I is less than 25, add +1. And the other thing is the 0.1 that you see at the very end, that is connected to the command with color. The first condition, if I is less than 25, add +1, make sure that the subpath is at least the half of the path. It doesn't seem to be necessary, so if you just delete it, you will not notice very much. But if you zoom in very, very much, you will notice that it's very inaccurate at the ends. So it's important to have this part. And there's also the other part. The mapping to the color has been done in a way that the curvature of 0 is yellow and the curvature of plus or minus infinity becomes red. So I needed a function that changed the green part of the red, green, blue part of the color. And the function is defined as follows. And the 0.1 changes the speed, how fast the curvature becomes red. If we now analyze example MetaPost paths like this, here a path that starts in Z0 heads to the left, passes through Z1, and ends in Z2 with the direction to the right. Then we can add a curvature comb, and we see that for each segment, the curvature is naturally constant, so it's smooth, but there's an abrupt change in Z1. In fact, MetaPost tries to minimize this gap by calculating the so-called mock curvature and choosing the angle where Z1 passes in an optimal way. But because it's only a Taylor approximation, because it's only approximatively continuous, you still have a gap. So this is described by John Hobby. And if you fix directions, so here the direction in Z1 is fixed, that it must head down, MetaPost has no way to optimize curvature, and things often get worse when speaking about the curvature change in the connecting knot. So Z1 here has non-smooth, well, it is smooth, but the curvature is not continuous. If we move this knot along its tangent at the right place, we can make the curvature continuous, and that's what some people call harmonized. So I just took over this term and also call it harmonized. And I've written a macro that works like here. You write harmonize in front of a path, and then it harmonizes it. And often people say, hey, why should I use it, harmonize? I mean, it looks already good. And probably it does, but it never harms to consider it. So to the left is a bowl of a J, and the not harmonized version has is not continuous in curvature, and the right version is harmonized. At the first glance, they look very similar. So here's the magnified version, and also the definition, just in case you want to test it yourself. So this is the original, and this is the harmonized. And I've also inked versions of it. This is the original, this is the harmonized. And if I switch back and forth, you see it hardly changes. And here's also the logical difference of this both area. So you see in some parts it differs quite much, in other parts it doesn't differ. Of course, one could say, okay, if these changes are so subtle, why should I change it? I mean, I cannot tell you you have to do it, but maybe you think, oh, well, it could be a good idea. Here's another example of a calligraphic dot, so a dot that is not exactly circular. And to the left, there's the original version, how it was defined in MetaPost. And to the right, it is harmonized, so the curvature is continuous. And you can see that harmonized paths tend to be more rounded. And one could also say they lose a bit of their character. So maybe here it's not a good idea. So it's up to you to say what dot you like more. Again, here is the inked version of the original. Here is the inked version of the harmonized version, and I go back and forth. So here you can see the difference is quite bigger. I will shortly present the method of harmonization because harmonization was a tool that just appeared in closed software, and I couldn't find the proof of how it works, and so I will present to you shortly. The generic case is that you have two segments that join in the point G and 0, and we assume that they have the same direction in their joint and that there are no zero handles, so that there are no collocations of control points, and there's no inflection point in their joint. So we can assume that it looks like this, and the goal is that we move the joining knot in the right place such that the curvature becomes continuous. And for this, we have to calculate the curvature to the left and the curvature to the right. So again, I won't go into detail, but taking the formula from before, we get that the curvature to the left only depends on the height of the point R here and on the x coordinate of the point P here. And the same for the right part. Again, it's just filling in the formula. And if we want to have both curvatures equal, this comes to this equation with the solution for G is either I divided by 2, so it must be in the mid if D and L are equal. And in the other case, it's this special formula, D plus minus square root of DL over D minus L times I. And the nice thing is that the square root of D times L is the geometric mean, so this makes sure that the solution is always in between these control points, so you don't get strange things out of it. Another nice property is that the curvature at the other ends, not the joining ends, but the other ends will not change. So it's very easy to make a global solution, so a global continuous, curvature continuous solution. So if I change back and forth, you might notice that at the very left and the very right end, the curvature was not changed. So how does a global solution work? Like here in the dot, I have also displayed in black the control points and the handles. So this was not the not harmonized version, the original version. And here is the harmonized version. And you see only the joining knots have moved along their tangents. There are some special cases that have to be considered. One special case is if either D or L is 0, so if one handle lands on the tangent line, then the new G becomes 0, so you have the problem of collocation. In type design, this is normally not desirable, and because you will infinitely large curvature. So this should be avoided. And there's another special case where you have a point of inflection as the joint. So then the curvatures must have different signs because this is the definition of a point of inflection. But different sign and equal means that they must be 0. If you want to have them to be curvature continuous. And so we must have these handles to land on the tangent like this. We could also move the other handles additionally and still get a curvature continuous solution and make it area preserving, for example. But there are some problems that come with it. One problem is the rounding problem. So you always have a rounding on a grid, so like a smallest number. And so here you have an original path. So this is a curvature continuous solution. And this would be perfect, but now after rounding, of course, it won't be perfect. And here in this case, it adds an additional inflection point. So it's probably not desirable, and it works different than the solution that I presented before, because the off-curve points are changed and not the on-curve points. If we have inflections, it's better just to make the absolute value of the curvature continuous. So this is just a mirrored solution of before. So this is the easy case, and this is also the way how FontLab handles this problem. So here I define harmonization is the act of setting a new G depending on these coordinates, as I said before. And here is the macro for MetaPost. I iterate through the joining nodes of a path, then I check if the joint is smooth at all, so I only apply the change if it's smooth, then calculate the new position as described before with this formula. I also have to check if the path is cyclic, then the last point equals the first new point, and at the end I return a path that is made of these new joining nodes and the old control points. So this looks like this. Again, if you want to study it in detail, just look at the preprint. And I found out later, after I have developed this formula, that in 1990, Robert L. Roach and John R. Forrest already published an algorithm at the NASA Langley Research Center to make exactly this thing that I wanted to, so to harmonize it, but of course they didn't use this term at that time. And it's equivalent, the algorithm is equivalent, but it works slightly different because it depends on an intersection point D, and this intersection point does not always exist. For example, in this case, you would have the intersection point D in infinity, so this would not work with Robert L. Roach's solution, but it works with the solution that I have presented here. And there are some plugins that use the Roach algorithm. For example, for glyphs, there are two plugins, the SuperTool plugin and the Green Harmony plugin. Both use the Roach algorithm. The SuperTool has it slightly modified. In 2010, the font remix tools have introduced a harmonizer, and they defined this term, but it's closed source, so I cannot say how it works. But I can say that it probably works different in some cases, at least from what I have seen. And in 2017, FontLab 6, and now also FontLab 7 and 8, have a harmonized tool, and it's again closed source, so I cannot say if it's equivalent, but it seems like it works just the way as my algorithm that I've defined here. I have also written a plugin for FontForge, and finally in 2020, I have directly patched it into FontForge. So FontForge now also has a harmonizer. If you use current version of FontForge, you may use it yourself if you're into font design. And still, of course, it has some disadvantages. One disadvantage is that the harmonized path do not longer interpolate the points they were originally meant to. So here, the original point Z1 is not passed anymore. So I once came up with the unfortunate idea that I could make it super smooth, so I would not move the joining knots, but the control points that are off curve, and then I could satisfy even more properties, like not only the curvature will be continuous, but also the change of curvature will be continuous. And I called it super smooth. And it was not a super smooth ID because it has some problems. It could introduce new inflection points, and it was very hard to globalize. So by changing the points for 2 segments, everything changed globally, and the whole situation had to be calculated new. These are the references, and I'm open to questions.
Okay, thank you very much. Are there any questions? Okay, there is one.
Does your technique conserve the total curvature over the entire curve? So is the integral conserved?
No.
Because I think that may be a solution to your problem of the harmonized glyphs losing character if you conserve the total curvature.
There are several properties that could be taken care of. So the total energy, the total curvature, the total change of curvature, the preserving of the area, and actually I didn't think of the total curvature. Maybe I have to consider it, but it's indeed the case that I do not have a satisfying solution for this. So if anybody of you has a good idea, like you, how this could be reached by setting the offset points to get a global curvature continuous solution, I would be very glad to hear your ideas.
Okay, we still have time for questions, if there are any. Yeah.
So thank you for the talk, and I was wondering why you chose to place a new joint point on the tangent line and not on the curve, the G nu.
So you mean it would have been better to wander along the curve and take one of these? Well, the first question would be, on which side would you wander? So would you go, in this case, would you go up, would you go down? So this would be a first problem, that it would not behave symmetrically, I guess. But of course, it would be possible to take a point that is near and redefine the other segments. But yeah, it's not symmetrical. This is very unsatisfying, I think.
Okay, if there aren't any more questions, I don't see anyone. So thank you again for your talk.